Let's welcome Richard to the podium. It's yours time now.
Thank you. Thanks. Before I get started, I want to thank everybody who's here and everybody else too who signed that letter to support of gold. So I really appreciate that. It was really, and it really made an impression. I know on people at headquarters. I talked to some people and they were really impressed with how many people had signed that letter. So that was great of everyone to do that, including the ones who aren't here this morning. All right. Let's see. I need to project here, and I'm not projecting yet. I get this. I do this. If I do, so go to slideshow. It does it. Is that what I need to do here? Let's see. Okay. All right. Okay. There's the cursor. I found the cursor. Romina tipped me off on that. Okay. It worked. All right. Okay. I chose a rather ambitious title. I'm not sure I can live up to it, at least not in 20 minutes. And I will only hit on a piece or two here that I think of stuff that I think is important. So I sort of, just sort of ask it as a question: why has prediction been so elusive for us? And I think we all come up maybe with there's multiple things we could come up with. And I think one of them, of course, I would always say is spatial. Temporal resolution and stuff like that, but one of them is definitely just the lack of neutral temperature information, which is something that gold has we've been able to do with gold and been able to see how important it is. And part of the reason I say that it's so important is that it's really is a fundamental variable for the thermosphere. I think of the thermosphere as being pretty close to an ideal gas, and I think of it as usually I've said something about how you got temperature and composition, but it's a triad: temperature, composition, and density. If you've got two of those, you really can get at the other one. So, but since we want density, if you have the temperature and composition are really a path to getting that, and those are the two that we can certainly remotely sense over a large area, spatially and temporally. So it really is, gives us a lot of leverage on understanding what's happening. Of course, as we'll get into here, one of the issues with doing large scale is you basically are viewing down from some higher altitude, and you really are sort of sensing a relatively narrow altitude region or somewhat limited altitude region. So anyway, it's I think the composition being essential. And of course temperature's being essential. Composition is essential too for understanding a lot of stuff. And we've had that for decades. And I think time has really been a really great mission. It's really shown us how valuable this is, still providing data. So I think this is just one of a storm back in 2003. This is one of the really huge storms that people have still been writing papers about. So, it's really been a fabulous mission. And basically we get, it gave us night side density, electron density, day side composition. And timed MINI, Icon MINI also did some temperature information in the limb. This is actually it's 2025 GRL. I pulled this from. I went looking for some data from they had I guess in the limb, they were looking at about 80, 90 to 100 and 130 kilometers. So they get the temperature. This is a magnetic storm and ascending and descending tracks back in 2021. So, and it also had composition, of course, with a different instrument. So did have a nice combination. And it was I was really looking forward to doing, working more with ICON data. And I think as everyone else was, it's very clear from last night, since ICON was the most popular mission of all. so I think it was a huge loss for the community, certainly. So, of course, gold, with the composition and temperature, it's been really, we've been able to keep operating, observe some big storms, and these are definitely important, having this combination. So just to sort of always the question has been exactly, in my mind, is how important, relative importance of composition, temperature, and all these things, lower atmosphere. If you try to do a simulation, you can test this with an OSSI, observation systems simulation experiment. So you can simulate data, so you know what the data, what is in the, what the components are, what the changes caused, what components change the data, and test it. So Fazlul Laskar, one of the guys who worked on the gold team, did this with, he and I think Nick was involved also, an OSSI, and they simulated gold data, composition and temperature, and also they used lower atmosphere data. And you can see here, they included the different pieces. It certainly improves with composition data, but it improves even more with the simulation of just the temperature data. And of course, the green line is the truth, so if you're able to simulate sort of all these pieces, you could get to that green line. All right. Now, so I keep talking about the density, so, how well can you really, okay, if we're looking at 160, how well can you really do on the density is one of the questions that is an obvious question. So what Fazlul did, he did this, and actually, since you got the like empirical models like MSIS that are based on neutral density data, they use, of course, to give you a temperature, but you can turn it around, since it's got that temperature-density relationship, you can turn it around and say, okay, if I got this temperature at 160, what is the density at some other altitude, which is what he's done. And he'd done this earlier for the SpaceX storm, the minor storm, and the shown here is the results for that Gannon storm. So basically, it's pretty close to Grace Fall Zone, which is sort of about as good information as we have about the density. This is sort of an average over the day for the density. And so at 480, he gets certainly a much better result and seemed like what you expect to get, or would probably get from MSIS model run alone without any other information. So, of course, I guess everybody should probably knows the reason this has gotten so much interest about density or neutral drag lately is because all the satellites is one of the reasons that this has gotten a lot of attention. The SpaceX, they keep putting up twice a week, they're launching stuff out of Kennedy Space Center, maybe even a little bit more often this year. And so there's a huge number of satellites they're putting up. So not all of them are, of course, SpaceX Starlink satellites, but a lot of them are. And Amazon, I guess Blue Origin, Jeff Bezos, is he's working on building another system like that, as I understand it. So there's going to be even more. So, of course, there's more objects up there. They have to do more maneuvers to sort of maintain orbit and avoid collisions. And it just gets to be, it's growing very rapidly. So, of course, as we know, there's certainly a submission. I think GAU showed this. This is some work by him that used the Wacom X model again and just kept the KP constant, F10.7 constant, and just looked at how much variability you got at 300 kilometers. I think this is a SD Wacom X, so basically you're sort of driving, got some of the lower atmosphere stuff in there, and sort of seeing how it's, how much variation do you really get at 300 kilometers? And it's about 10%, which may not sound like a lot, but for really quiet conditions, that's a significant amount of their uncertainty in the orbit's information that amount of density is. So, okay, yeah. So density, satellite drag. Okay, so what? Well, temperature also reveals your wave dynamics. It's responds to that. But as we know, it's complicated because as you go up in altitude, different waves break and sort of crest and get to different altitudes. So it's a very complicated picture. And I think that's you sort of see that here at the different altitudes. This is just again, a model, some model calculations about what the wave perturbations would be. And what doesn't look very significant at 80 kilometers may be very significant at when you get to 200 or 150. So it changes pretty rapidly with altitude. So that was the motivation. Using the temperature was really, again, was the motivation for AtmoCube mission. Be able to use the temperature to remotely sense, to look at the waves in the structure in the atmosphere. So it uses the O2 atmospheric bands, it uses 2 interferometers and tomographic oversampling. And this actually, I just got this, I think, yesterday. This is at least at the moment, this is the best image I have of the satellite. It's with the solar panels deployed, and you can see the 2 instruments there with the apertures for them in the front. Just to give you a little more information about it, it's a 16U satellite. It has 2 interferometers, 2 small interferometers. It's an H-Fort mission, and NASA, I guess it's NASA funded by the NASA H-Fort mission, and University of Colorado is building the satellite bus and doing the detectors. Ulish Research Center is doing the interferometers. They've made these, flown these before on rockets. They've never flown them, it's never, at least haven't been successful at flying them on a satellite yet. They had some on one satellite, but unfortunately the satellite failed. Wasn't successful. So just to give you context here for, shows where all measures about 80, really it measures about 85 kilometers, more or less, but AtmoCube will measure about 80 to 120 kilometers is what we're doing. Now, it's a technique that it's O2 A-band emission. The same thing, actually it's the same thing essentially the same thing we do on gold. We're looking at N2 emission, just looking to how the band structure changes and how the brightness of the rotation of the envelope changes with temperature, and you can do the same thing with O2, which is what we're doing. So just do a retrieval of the temperature from how the spectrum changes with temperature. And the instrument, basically, it's sort of mentioned, I think I had a poster a couple of days ago that showed sort of how small it was. It's basically had to compare it to a dime. It's really pretty tiny, the heart of it is, but just a couple of gratings, and you basically put it's a narrow field of view, you got a beam splitter. Anyway, you can get an interferogram, and from that you can get the spectrum. Each of the 2 lines, each of the 2 spectrometers, the field of view is split, so you wind up with two vertical, different. I guess like you split the field of view, and you wind up with basically 2 spectra, 2 samples from each interferometer. From the 2, you get 4, by having 2 instruments, and from that we're using it to give us cross-track information. As you fly along, if you do the sampling fast enough, temporally you get long-track information. So we're doing that such that we get about 30 kilometer resolution. 30 kilometer sampling, I think specs works out to be certainly a little less resolution, but 30 kilometer sampling, I should say, and 2 kilometer sampling vertically. The ranges that's remotely sensing there, it does do day and night, so you're looking at that 80 to 120 is the daytime. At night, it's really less than that because of the mission, where the mission is. And the idea here is that the Germans have been pursuing is to do sort of a 3D recovery of what's going on by looking and using the multiple lines of sight as you fly along. So, oops, I'm wrong direction. Okay. All right, so the vertical coverage, of course, there's about 40 kilometers, 80 and 120 there. The resolution we expect to be about 100 kilometers in horizontal and about 6 kilometers in vertical. And that should be sufficient to get a lot of the gravity waves, some of the smaller gravity waves we're targeting. And by looking at the spectra, looking at the temperature changes, the approach is to use those temperature changes, the temperature gradient, to get at what the momentum flux is. I think one of the key references is this Vadas and Nichols. There's certainly, in 2012, there's been it's laid out a different set of relationships, there's a different set of parameters it use, but the same things they talk about in there about using to get out some of these quantities, you can do if you have the temperature gradients in 3 dimensions. So that's what the approach is being used, to try to do the temperature gradients in 3 dimensions, along track, cross track, and vertically. So if you get that combination of measurements, you can get out the momentum flux and its divergence. And of course, this is something that, this sort of the wave-induced drag on the mean flow is something that isn't captured in the models. None of the empirical models include this. You either go to HASNM, MSIS, none of those models include that. So this would be something that, by looking at this, we can we're going to, the idea also I should mention here is we're going to a precessing orbit. Idea is to go to about a 45 to 55. We still have to work the details of that because, we just have to hitch a ride on one of these launches that's going to space for something else. And a lot of the CubeSats, this is a little bit of a departure on the CubeSats for LASP, because almost all those CubeSats that we've done, as I understand it, have been sun-synchronous orbits. And it makes the solar panel configuration much simpler. And that's been one of the challenges it took us a while to work out, is getting enough power, when you to keep operating pretty much full time. There'd be a few times when, you're doing downlinks or data and stuff, but pretty much the idea here, the way we got it laid out, is we're able to operate almost, not continuously, but most of the time the satellite will be making observations. It has power to do that. So anyway, the mission, we've always all heard of this, lower thermosphere gap, right? So this sort of fills that gap at a time when we don't have observations in that gap. The launch date is supposed to be about late 2029. I guess of course, if this works well, the CubeSats are pretty cheap. The total budget for H4 missions allowable budget is $10 million, right? At least from NASA. So and the instruments contributed, but there's not a lot of resources on their end either that's necessary to do it. So if you can do this, you could actually deploy multiples of these and do a much better coverage spatially and temporally than what you can do with just one satellite. So it gives you the combination of measurements. So I guess, the question is now, I'll ask, what else are we missing? I sort of laid this out. And, the thing we're missing is really what you really want to have is a continuous, like the wind, you want wind and full altitude profile of composition, right? So we sort of don't have, 2 minutes. And that is coming with dynamic. So I think, 2029 we'll have, of course, AtmoCube will be flying, and after that, as we know now, dynamic is coming. So I think I think I have 2 things to look forward to, is AtmoCube and dynamic. So with that, I will close, and thank you. All right.
For Richard?
Is this one working? Okay. Do we have any questions?
For people online, please use Slido. I haven't seen
Richard,
anything.
can I ask a question?
Yes.
Great talk. Thank you. So maybe you mentioned it and I missed it. What is the duration of your mission?
Well, these CubeSat missions aren't designed for a long duration. I guess the 6-month primary mission, but then, of course, we hope to keep it going longer. And some of the CubeSats that LASP has flown have flown much longer than even a year. So, hopefully we can keep it going for multiple years. It's low Earth orbit, so it's not the radiation is bad. They do, the engineers, this is one of the questions that the Germans are asking about it, and we always tell them that, okay, it's a 6-month mission, but everything, LASP engineers, they designed it to keep lasting and lasting. That gold was really a 2-year mission, and we're on year, 8? So, yeah, and still going.
Okay.
And hopefully a lot more years with gold.
Okay. If there are not any other questions, I'll ask.
Thank you. Great talk. What's the orbit that you're targeting with this?
It would, it's about a 500 kilometer, 550 kilometers. You have to, with the CubeSats, you have to have a orbit that will deorbit within a certain length of time. So you're pretty much, unless you have propulsion, you're pretty much limited to something below 600. And of course, you want to be a little bit higher so we can do, all the limb viewing and not come down too fast, right? That's one of the limitations. And I guess the fortunate thing is, in a way, talk about that, is that this will be at solar minimum, which is a great time for seeing waves, number one. And number two, it's when you have less drag and your satellite isn't going to re-enter as fast. So maybe we'll see how long we can keep it going. What inclination? I'm sorry? A 45 to 55 is what we're looking for. We didn't want a sun-synchronous orbit because we want to walk around and then you can see the tides also. And that's help you get out, understand what the winds are doing. Yeah.
You have one more?
Yeah, I have one more question. So you mentioned tomographic reconstruction.
Yeah.
How long does it take for you to take one image?
Let's see. I've forgotten what the sampling. We're doing sampling at about 30 kilometer intervals. So basically, it's a few seconds, right? It's where it works. I think it works out to be to get to 30 kilometers. So that's so each image, basically think of it as an image on the detector. It's about, a few seconds is really what we're talking about.
Okay. And so you're using a few seconds of data in order to, and invert that in order to get the information.
Well,
on
yeah,
estimate?
combinations of them, right?
Okay.
Because you got multiple views as you go along. So, of course,
Very
there's limitations to tomography, and with limited fields of view also. But that's the approach that they've been working on or been using.
Very nice. Thank you.
Plan to use
All
some
right.
data.
All right, so we have to move on.
Okay.
Thanks very much, Richard.
Okay, you're welcome.
So next 1 hour is Christina. So we are going to talk about CEDAR science going forward. So for people online, please post your questions using Slido.
So while we're getting this set up, I'd really like to encourage those of you way down there in the hinterlands to come join us over here. It's a lot easier for the speakers to only talk to one side of the room. So come on. There's a whole lot of room over here. Okay.
Should I stand here?
Can you? Yeah. Wait for people to. In my classrooms, I don't let anybody sit in the back of the room. So. For those of you I haven't met, my name is Christina Lynch. I'm at Dartmouth College. I'm on the CSSC for another 3 hours. And so I wanted to give us an opportunity at the end of CEDAR to think about what exactly CEDAR is and why we're here. So the goals for this session is to, just stop and think, what is CEDAR science? What has it been? What should it be going forward? So we'll look at the decadal survey. There are documents that sort of describe us. We should think about whether that works. So the decadal survey provides a narrative of science questions exploring the regimes that we explore. So sun-Earth system science, plasma physics, space weather. And then there is a CEDAR vision document that provides a listing of research themes inside our purview. Geospace systems, boundaries, evolution, observations, instruments, disciplines, data, models. We do a lot of stuff. So the question is, how do we define what we do? That's an important question. Otherwise, you just sort of wander. What are questions to consider and directions to explore? So our outline here is, first, Romina is going to describe just looking at recent history of how people have defined their workshop sessions. It's kind of interesting. And then we have a few examples of what people are doing or about to do. So Mark will talk about distributed instrumentation and how important that can be. Bill Swartz will talk about a new mission that's up there right now called EASY. I tried to find somebody to talk about AI. It's a huge, big field, and a lot of us don't know much about it. So Kike will give us an introduction to what can be done and is being done with AI. And we'll finish off this hour with a look back at the decadal, and then a recently added introduction to the Daphne mission to those of us who aren't familiar with it. So Romina, I'll let you start. Oh, and let me say, actually I have it here. So we use this hour to introduce these topics. And then we have a follow-on workshop around the corner in 101, where the first hour is a sequence of presentations on some new things that people are doing. But the second hour is basically a structured discussion. So you've got an hour to think about, what questions, what would you like to hear more about from these plenary speakers? And that's what the second hour will be, and that discussion will be around the corner here. All right, so Romina, up to you. Yeah.
All right, good morning, everyone. So I would like to start with this. Okay, let's go back to this one. How many of you know about the research, the CEDAR Research Trusts? Okay, all right, a few people. So these are, for those of you who do not know, these are the research trusts that were defined in the 2011 CEDAR vision document, the new dimension, and here they are. Basically, the first one is about the systems perspective of geospace. The second one is processes at the boundaries and transition in geospace. The third one has to do with the geospace evolution. Fourth one is the observational and instrumentational strategies for system studies. 5 has to do with the multidisciplinary nature of the work that we do. And 6 is the managing mining of data models. Okay, so these were defined in 2011, and I think right now, actually, especially for people who are have been coming to the CEDAR later, probably everyone has a different interpretation of what these research thrusts are. So in CSSC, we have a strategic vision subcommittee, and we were looking to see how people actually use these RTs, like how these RTs are being used in our community. And we learned that one way, actually, which might be the only way, is when you propose a CEDAR workshop, you're asked to select up to 2 RTs that is most relevant to your workshop topic. And that is, that is the only way that we could find that these RTs are used. So we looked at the distribution of how these RTs are used in the workshop through the years, and we had the information from 2022 up to now. So we have 5 years of data that we can look at, and I will present a summary of that. But before, let me tell you a little bit of methodology so that you don't get confused. So for each workshop, we have up to 2 RTs that could be designated, selected for those. These are very subjective. So depending on how the main convener of the session sees the session, they might choose up to 2 of those research thrusts. There are some workshops that have only 1 RT selected, and there are fewer workshops that only have no RT selections. And to do this analysis, we treat each RT as one data point. So the total number of RTs is not the same, is higher, about twice as much as the number of the total workshop. So please keep that in mind when we look at this. So this is a pie chart for distribution of the RTs for 2022. the first, and everything starts from the top. First, the blue is the system science. So, and then we have the boundaries, we have the evolution, in orange 19 in instrumentation, observational instrumentation strategies. This darker orange is multidisciplinary, and then this turquoise color is mine data models. And we can see that, so this is what I want you to take away from this picture, basically, is the relative, relative percentages of the RTs that are being used. And you can see that, from 1 to 5, relatively, you could say that is a uniform distribution. We have a very small number, maybe 1 or 2 workshops that will have to do with have selected the mine data models. Okay, so now let's look at 23. We do not see significant change in 23, about the same. 24, we see slight inclination toward more of the first 2 and first 3, actually. So the first 3 RTs have more with the scientific nature of the workshop. 4 and 6 are more have to do with the techniques, and 5 is multidisciplinary. So looking at these, what I found was that the multidisciplinary had to do with education and also some sort of earth science. I thought that if we have machine learning, it will be mine related to RT6, which is mine data and model, but that was not necessarily the case in how the community has selected those. So we see that in 24, we start to see this trend that we're going more towards the science. And it looks like that the system science approach or topic or research thrust is is better or more used basically in the workshop. So everyone most of the people, when they submit their workshop, they say, okay, we are doing system science. This is 25. This was very strange to me. You see that about 75% of the total distribution, 70% of total distribution is 1 and 2, with some of the 3. And this is the CEDAR JAM joint meeting. So maybe that is why we have more, towards science related workshops. I don't know, but it's a lot towards system science. It looks like that everything we do is system science. And this is 26. More or less the same thing. We see more instrumentation, and I will go over the list of the workshop that have identified the instrumentation to just give you an idea of how people, select these. But the main takeaway is that it looks like that there is a consensus that most of the workshop that we are doing is system science. So, okay, so this is another view. This is a list of the workshops that have identified 4, for example, the instrumentation and strategies, and which I found interesting. So we had 26 workshops, 11 of them had identified 4, and there are 3 ISR related workshops, specifically on ISR, that are 4. So, and then the equatorial aeronomy workshop, auroral science, machine learning application, observing and modeling mesosphere, lower thermosphere. Okay, you can look at that yourself. But we had a larger number of in the instrumentation thing. So here's a question. We see a higher level of inclination for the system science. And so everything that we do is system science now. I think it's well established. But does it mean that it is too broad of a research thrust for us? Does it, if everything we do, most of the things we do is system science, is it specific enough? Or is it intended to be broad in the first place? I was still a graduate student when this new dimension document was being written, so I really don't know what was the intention behind it. So at the breakout session at 10 o'clock, we will revisit this, and we'll see that talk about the future. When we talk about the future of CEDAR and where we are going, then what are the gaps that we have? What are the things that we do not do right now, and then use that to maybe modify these research trusts. So we'll talk about that. So please attend that session if you can. Thank you.
I think while we're shifting over, if somebody really wants to bring something up right now, but I would encourage you to think about these and bring them to the workshop later. So our next up is Mark, and he's going to talk about distributed systems.
All right, well, thanks, everybody. So this session is about CEDAR going forward, and if you look at the 2024 Decadal Survey, one of its top recommendation for the NSF Major Research, or MREFC, which is Major Research Equipment Football Club or something, its major recommendation there is for this distributed array of small heterogeneous instruments, ground-based instruments that would operate as an array. So I've grabbed some of the descriptions there. And an important thing to note is, although the description is quite ambitious in the Decadal Survey 2024, describing new facilities, the intention is also to build on existing DAISY networks and existing individual instruments. So let's see. This is a picture from the Decadal Survey. Again, it describes a rather ambitious implementation of DAISY, but something that covers North and South America with maybe 30 or so observing sites, overlapping fields of view, multiple instruments there. And again, the important point here is that these things would not replace existing instruments, they would augment them. So if the Decadal Survey means anything, we need to think about how this would fit into the CEDAR going forward planning. I've grabbed a couple of examples. If you look for where DAISY is recommended in the Decadal Survey, it's recommended all over the place, and it's described all over the place. So I'm not going to read all these out, but there's a number of recommendations in there for a, not DAISY, DASHI array. The difference between DAISY and DASHI is the H. H stands for heterogeneous, and that's an important thing. It means that these ground-based facilities don't have to be all identical, but they have to work together. And I want to actually just share a personal observation. DASHI is about ground-based instruments, and I started in the early 1980s running a Fabry-Perot spectrometer in Antarctica. The picture on the left shows the periscope that viewed the sky from that instrument. And I got a bit despondent as a graduate student, thinking that my one instrument in Antarctica could view just a tiny little patch of the thermosphere. Contemporaneous with that was the Dynamics Explorer mission, and DE2 was mapping winds over the whole globe. And I thought, how can I possibly contribute? How can I be relevant when there's this spacecraft covering everything, and I've just got this one little spot? But what I didn't realise, and it actually took me probably 2 decades to realise, is that the two instruments, the one in Antarctica, the one in space, they're just taking measurements as a function of time. They're following different trajectories through 4-dimensional space-time, but they're not collecting more or less, at least to first order, than each other. They're just focusing on different things. So sure, a spacecraft can give you global coverage or large area, but what a spacecraft can't do is it can't sit there and it can't measure the time derivatives in that one spot. And the time derivatives appear all over the place in the Navier-Stokes equations. They're really important. So ground-based equipment is that spacecraft get all the glory, but ground-based equipment can do just as important science and for a fraction of the cost. So I've listed some benefits here of the ground-based instruments. You can get long time series observations from which you can find time derivatives. As I said, they appear in the equations and they're really important. You have a mostly unconstrained budget for mass and volume at least, and probably for power, maybe not for data bandwidth, but for mass, volume and power there's no constraints. They're repairable and upgradable after deployment. Low cost, I calculate roughly, order of magnitude calculation, I could deploy 1,000 DASHI sites for the cost of the originally imagined GDC mission. We're not going to do that, but that gives you an idea of the relative scale here. Lots of broader impacts with ground-based instruments, so I probably don't have time to go through those. Talking to NSF, the other thing that is abundantly clear is that anything we propose, and particularly anything of a large scale, has to address the current federal research priorities. And what that means for NSF right now is that, something this size will have to have some connection to artificial intelligence, quantum computing, and or space weather. Fortunately, DASHI would hit 2 of those 3 bullets. A big, large data system like this is just what you need for artificial intelligence studies, and of course, space weather's a no-brainer. So I wanted to pivot and say, how would we actually move forward with this? Clearly, as I said, if the decadal survey means anything, we have to have some plan to address this. So there's 2 basic models. In the decadal survey, DASHI is envisaged as an MREFC project, a large monolithic project with a single lead institution, maybe some co-institutions, but one project that would be implemented as a monolithic entity. But alternatively, you could implement DASHI in the distributed part could also be part of the distributed implementation. You could have just a series of cooperative awards in which individual PIs and institutions build a piece of the array and then work together to make it into a coherent whole. The benefit of that second model is that you can build something like this incrementally. NSF doesn't have to find one large lump sum to fund it. It can be done incrementally. It's not dependent on a single PI or institution for initial or ongoing success. You can incorporate existing DASHI arrays and other instruments easily into a model like that. You can more easily assimilate new instrument concepts as they come along, and the array can be successful as a whole even if individual nodes come and go. The problem with that is it risks just becoming defocused and not a coherent whole. So in order to make some sort of a distributed implementation model function as a whole, you need some glue to hold it together. I've identified 3 things that I think would help with that. One is a well-documented, easy-to-use data system that allows all the measurements to be seen, to appear to outside users as a single entity that they could query and use together. You need a baseline set of geophysical measurements that would be they don't have to be available at every site. If there's an existing legacy site that we want to bring in, we can do that. We don't have to force them to add all the baseline measurements, but we should at least try to get most sites to have the most important measurements available there. And another thing, just on a practical level from my own experience, I think if we're going to build something of this scale, it would be helpful to have some sort of a logistics support contractor that we could go to as we need, piecemeal way, who would have a standard observatory enclosure that they could build for us, they could deploy for us, they could deal with things like site usage contracts and permits, and they could help with shipping, installation, commissioning, that sort of thing. I know nothing about data systems really, but there's a lot of them out there. There's a session yesterday, I think, on data systems. It's clear there's many options, Madrigal, Zenodo, AWS, lots of others. I'm not an expert, but what I do think might be possible is for the data system not to be one single repository. The data could be stored in multiple places. What would make it a coherent whole is if there's a consistent set of APIs that a person can use to query wherever the data is. If we've got a consistent set of APIs, you can pull the data from where it's stored. Others know much more about that than I do, but that was a thought that occurred to me. So final thoughts on this model. If we do it as a distributed way, it would require almost no special effort on the part of NSF. It could be built using the existing proposal, geospace cluster proposal route that we have now. The one thing we might ask NSF to do is to add some words to future solicitations that say that review panels could identify DASHI relevance as a potential strength in review. And sort of an upbeat note, I think DASHI could become almost a whole of CEDAR endeavour. Not that everybody in CEDAR would be working on it at once, but it could incorporate all the things we do in CEDAR, the data science, instrumentation, observations, modelling, and maybe even theory. It's a way that we can all work together. It would leverage existing expertise, provide lots of opportunities for students to get into the field and get experience. It has obvious relevance to those priorities of AI and space weather. And my final thought is related to Larry's talk the other day. You know, I see Dashi as something that would actually be an implementation of his oak tree model, where we all work together and collaborate on a coherent next generation capability for CEDAR. So I'll stop there.
So if anybody has one question while we're switching over, and Bill, if you can start wandering up here. Here, you'll probably have to talk to this.
All right. My question is, how do you foresee that we implement this as a community? Do you think that we should have maybe a special call for a facility-style thing in which the community gets together and, you know, propose it much like we're proposing for space missions? Or do you think that we should just piecemeal this thing in place, following a certain plan?
I think I have about 7 seconds to answer that. So I don't, the idea that I'm suggesting, and don't believe that this distributed model is what we should do, it's just my suggestion. In that model, we don't necessarily need a special call, we just build it up in pieces using the sort of existing routes we have. The one thing that we might want to consider is whether we would have some sort of a steering committee, or a scientific steering committee that would have overall responsibility for perhaps contributing to the proposal reviews and reporting to NSF and managing things. But in the distributed model, I don't think we need necessarily a dedicated call. We just need it to be one of the review criteria that the review panels would look at. Oops, sorry.
That was my toe. Sorry. All right, so let's try and collect some thoughts on that during the discussion section. All right, so our next presentation is about the EASY spacecraft, which is actually up. Yeah, all right. I'll give you a 2-minute high five. Oh, thank you. Yeah, okay. And you just go forward with the thing.
All right, thank you very much. Figure out what display I'm going to keep an eye on. So yeah, today I'm going to be talking briefly on the EASY mission. As you probably know, EASY is heliophysics MOO. It comprises 3 6U CubeSats in a pearls on a string configuration and orbit. We're using differential drag to change the temporal separation between them in orbit. The primary science is MI coupling of the auroral electrojets. I don't have a lot of time to talk about the science today, given limited time, but I also want to raise some new directions for us that we're looking at with the EASY data, namely temperature and winds in the middle atmosphere. So all the EASY data that are currently publicly available are on the EASY Gateway. There we have level 1 through 3 data. We're working, it's currently version 2, we're working on a version 3 that will hopefully be out in just a few weeks. So just to remind everyone, the electrojets flow in the ionosphere, they perturb the geomagnetic field. You can measure those perturbations from the ground with ground-based magnetometers. They're about 100 kilometers away. You can fly rockets through. You can also measure them again with in situ magnetometers on spacecraft that are still, unfortunately, hundreds of kilometers away from the electrojets themselves. So EASY actually is a completely different approach to measuring those currents. We remotely sense them on orbit, taking advantage of the fact that the magnetic field Zeeman splits the 118 gigahertz O2 thermal emission, and from that we can infer and retrieve what the magnetic field is doing, including the contribution from the electrojets. And we are sensitive in close to the mesopause, just a couple tens of kilometers below where the electrojets flow in the ionosphere. So this is a new technique. It is akin to what we have used to measure the solar magnetic field for a long time, but this is the first time there's been a mission dedicated to doing this in Earth's atmosphere. So EASY, as I mentioned, is 3 CubeSats. So there are 3 CubeSats. Each has 4 microwave radiometers that have 4 different look directions, and each one of those radiometers measures the full Stokes vector. So from that, we can infer a lot of information about what's going on in the atmosphere. The 2D plot here on the right is from a single spacecraft. The rows are those 4 radiometers. The columns are the different Stokes vectors. So it's frequency on the x-axis, time ascending on the y-axis. So you can see how that Zeeman split changes with time as the spacecraft move relative to the geomagnetic field. So that gives you, that separation of the line gives you a sense of what the total magnetic field is. You can actually infer what the vector is based on combining the different Stokes parameters. There's also Doppler effects in that, so we can get some idea of what the line of sight winds are relative to the spacecraft. So again, not a whole lot of time to talk about the science. The primary science is auroral electrojets. So just one example, you can see in the plot there in the middle, you can see the 4 ground tracks, or actually the tracks at 80 kilometers of the 4 look directions from one of the space vehicles. The supermag plot on the right there indicates that there is a western electrojet present at that time. And the plots on the left are the residual magnetic field after the main field has been subtracted from those 4 cross-track beams. And you can see at the beginning, at the pole, so it's going from the pole toward lower magnetic latitude. It starts off pretty quiet, and then you see this enhancement of the magnetic field poleward of the electrojet, and then the corresponding reduction as the spacecraft passes through. So that is where the electrojet is. You can see it in 3 of the 4 cross beams in this particular experiment. But the spectra also contain a lot of other information that's useful to us. Don't worry too much about the details of the plots. These are basically Jacobians of how the radiance is sensitive to the temperature in the atmosphere. So we can actually have the basis for a retrieval of temperature profiles from the upper stratosphere to the mesopause in easy observations, which is very relevant. We've done some preliminary comparisons with these temperature retrievals with SABRE data, for example, and those results are very encouraging. The retrieval has lots of knobs, lots of constraints, lots of parameters, so we are still in the process of figuring out what the right positions of those knobs is so that we're not over-constraining the retrieval, so that's work in progress. We're also working on wind retrievals as well. So as I mentioned, that Doppler shift in the spectra that we measure can be related to line of sight winds. We have really good statistical precision, about 3 meters per second for 1 second, or 1 sigma, I lost the 1 somewhere, for 2-second integration. Again, this is also work in progress. Lots of things that we have to do still to work out some fine details of both the instrument calibration and our retrieval, but we're very excited about that as well. So big picture, this shows the separation during EASY lifetime. So we launched on the Ides of March last year. We are in our 3rd auroral electrojet season, so we do these at summer solstice when the mesopause is very cold and quiet. And the separation there between consecutive spacecraft went from about 2 minutes at the start of our first season up to nearly 10 minutes, and then we're bringing that back down. Right now we're like 7.5 minute separation using differential drag, so we can look at the temporal evolution of the electrojets at different time scales. But one of the great things about EASY is that we can essentially look where and when we want with the spacecraft to first order. There are some limitations, but that has enabled us to do some interesting special science experiments. We've done a number of CME storm chasings, and we can typically reschedule what the spacecraft are doing if we have a few hours of notice. It depends on the phasing relative to our uplinks, but with a few hours notice, we can typically, it happens over the weekend or the holiday, but we can change what's going on with the spacecraft, so we can look at the impact on Earth of a storm. We can have all 3 spacecraft in one hemisphere. We can have 2 in one in the other. So lots of interesting opportunities there to study how those storms are affecting Earth. We did last fall a dedicated experiment with HARP, where HARP was actively modifying the ionosphere, and we do indeed see that response in the EASY data. I realize that this slide title should have been nice and easy, but that's okay, next time, trademark. Earlier this spring, we coordinated our EASY observations with 3 rocket launches of NICE and BADASS. And we've also, this spring, done a number of collaborative measurements with the AW mission. So again, we can look when and where we want, so we can change the latitude, and we have roughly 100 coincidence measurements with the AW mission, which is measuring temperature at about 85 kilometers. We get the profile through that region, so we're really excited at possibilities for science there. So near-term future, version 3 of our data products are coming soon. They will include the temperature retrieval. Also some other details. We've updated the retrieval itself. There was a sort of artificial bias removal that's in the current data that we will be taking out, fortunately. And our prime mission ends in September, so we'll be proposing for extended mission very soon, and our intention is to focus more on sort of CEDAR relevant science related to temperature and winds, and again, have more opportunities for doing collaborative science with other experiments. So, thank you.
So again, if we have a minute while we're switching over. And also, I do want to say we don't have a dedicated discussion about EASY in the workshop, but I think Sam and Raphael are both here. Can you stand up so people know who you are?
Yep, Sam is
Raphael
the PI, by the way.
And Sam,
Raphael is
and so
executive
feel free
project
to talk to them during the break. Any immediate questions
Yeah.
as Kike's coming up? Yeah, go
I
ahead.
have a quick question. I was excited to see your wind and temperature products. My understanding of the EASY retrieval, which I don't understand, but to the extent I do understand it, you don't get a height profile. It's just some sort of integral over a layer. So what height would you assign to those wind and temperature measurements, and what sort of layer width you're integrating over?
Right, so that's great. So for the winds, that will be sort of where we're getting most of our information, like between 80 and 90 kilometers altitude. The temperature profiles, we actually, from the mid-stratosphere to the mesopause, there's enough information in the wings of the spectrum that we actually can get profiles of temperature.
Height resolved.
Height resolved, yep.
Right. Thank you, Bill. Okay, so next up is Kike. So, all right. And again, I'll give you 2 minutes.
Hello, I'm Kike. I work at the Haystack Observatory, and I'm going to share some explorations about the role of AI in our community from 2 different perspectives. First, how we can use AI to help us navigate the data, and how to use AI to do research. Okay, I'm going to, well, these are going to be the topics, but I'm going to jump through them a little bit faster. So first, a very basic introduction. So this is how this project started. We identified some things that we wanted to improve between the connection of scientists and databases. Things like how much the scientists can navigate the database, how much we can sample the interest of the community to improve the databases and educational materials, and so on. So we worked a little bit on visualizations, and this is TC data using cesium, but and we are interested in assessing the impact on research by using metrics on task completion. We are also building this agent that is called MADV. And the idea of MADV is to use a regular LLM, but with an additional architecture that uses curated information like Madrigal documentation, metadata, papers published with Madrigal data. And all of this was built using this app called Langflow, which it looks like this. So it's very simple. You can build it very fast. The difficult part is to accumulate the curated documents. And one of the things that we encountered was that metadata is very large, so we had to do a little, some tricks so the agent can extract only the information that it needs. The same thing with the papers. We synthesize the papers by topics, and now the agent has access to a summary of the papers following different criteria, so it can choose to what paper it can gather information to better answer the question. We are also using some of nudging from social psychology, but I'm not going to go into there. And this is how it looks. You can ask questions like, for example, what papers were using TIDs in 2024, studying TIDs. It's going to give you some alternatives. You can say, give me the command to download the data to reproduce the paper. It will give you a command, you use the command, and you can ask other questions like, I want, build me a Zenodo repository, right? How many days of ISR data were available in March 2022? And so that QR code is for you to test it, and if you want to give some feedback, you can use the other one, and that's online. We are also very interested in finding a systematic way to probe what the community needs, and if you are interested in this participatory process, you can talk with me after the talk. Another thing that we are exploring a lot is how to, now that because of this explosion of LLM tools, there are a lot of very sophisticated tools to take text and concepts and put them on vector spaces. And once you put it on vector spaces, then you can do all sorts of things with the concepts. You can find similarities, you can make clusters of topics, you can see how the different topics branch out of the clusters and so on. So here I'm showing papers, all the papers published with Madrigal data since the 60s, and how they move through the different clusters as the time passes. And you can do a lot of things with that. Like, for example, you can, in the plot to the right, you can see how specific clusters of topics evolve in time. But you can also see things like, for example, illustrated in the bottom plot, where you cluster the papers by methodology, and then you can see how they move to phenomena, to study of phenomena. And you can use that to build case studies, and case studies with a granularity that you can control. We are studying this to build training material, and also to do this, which is these three papers are talking about reconstructing Lyman density hydrogen from Lyman alpha measurements in fusion, in space physics, and in computer science. But if you take away all of the jargon, the mathematics is the same. So if you measure the distances between the topics, then, and you find that the methodologies that are very similar to each other, then you just pay attention to what is different, and those things are turns out that you can, those are candidates for new ideas for your topic. So for example, one thing that I'm doing is trying to use NERF technology to reconstruct exosphere distributions, and it's very nice. And another thing that we are doing is that when we synthesize the papers, it turns out that without noticing it, we build a training data for an agent to reproduce the papers. So we have a synthesis of what data the papers were using from Madrigal, what they did to the data, and the results on the Madrigal data. And that's basically a training set, right? So we tested the agent to build first a workflow, there a code, there an analysis, there an assessment of the results, and it can do it in a loop, and in each loop it can learn from the mistakes, and you can upload that to something that is similar to a README file, which is like a skills file, and this is an idea, a very clever idea from computer science community. It's an app called Auto Research. And so that worked very well, and we are starting to build this ERVs team. This is a ionosphere research virtual sidekick, and it's going to be composed by these different agents, each of them specializing in different parts of the pipeline. And the goal is to be able to reproduce all of the Madrigal papers that we can reproduce to attack two main problems. The first problem is the dark data. That's what astronomers call it, I think, are these data that are hidden in the databases that are there, but nobody's using it, and there's a potential for discovery. So the idea is that the agent learns how to reproduce the papers. It should be able to use that same methodology on data similar to the paper that they learn from. Also in the process, they should be able to build Jupyter notebooks and training material and so on. So this is the summary. MADV seems to be working. It has some bugs, so we would benefit a lot from your input, your interactions. If you interact with MADV, keep in mind that only has metadata of ISR. So we are putting more metadata, so you have to be patient with MADV. Then we are thinking of systematic ways to interact with the community, to gather information, to improve things regularly. And we think that we can now do science of science, basically, that we can operate on concepts. We want to think about Madrigal not only as a repository of data, but also a repository of ideas, of claims that have been made before, and scientific questions that can be tackled, but built using data-driven methods. And it seems that all of the evidence is suggesting that these AI tools are right now very good at building these structures. Yeah, thank you.
All right, thanks. We all have a lot to learn, and I'm interested, I think, during our workshop to perhaps combine the discussion of Mark's data system questions with your structures. So some questions for Kike while we're switching over? Anybody? One way down there.
Thank you, Enrique. Thank you, Enrique. We had a discussion with Asti and Leslie yesterday during the banquet about your work, and something that came up is that eventually when the agents do a pretty good job and we're satisfied that things make sense, it could be a consistency check, in a sense, for new publications that are submitted. You know, if the language is clear and explains what happens to the data, if you know, the agent cannot put together what has been done, maybe there are some issues with the reproducibility or with the language. And so something to keep in mind. Maybe one doesn't want to implement that too soon because it may create more confusion, but it's something to keep in mind.
Yes, I agree. One thing that I've been thinking a lot these days that I think is related to that is that it seems that almost like the papers are now a bottleneck. It's not the optimal way for the agents to exchange information. So I'm curious of maybe there's a better way that we can, as a community, like build, like what kind of structure should we use to avoid that bottleneck? Yeah.
It's an interesting question writ large. All right, so we'll have more conversation about that in the second hour of the workshop. So next up is Scott. And Amy, are you nearby? Where is Amy?
I think she's just in the doorway. Okay. All right, thanks everyone. This is going to be brief, but I'm going to talk about decadal survey, the science that's in it, the things that we should keep remembering, right? So especially for the students here who maybe haven't read this amazing document, if you haven't, it's very large. But what I'm really talking to is just two chapters, right? There's chapter 2, chapter 3. So chapter 2 trying to lays out, the community vision for science in the next decade. And chapter 3 talks about the space weather themes, the ways that our science contributes to helping technological systems, society, etc. Each of these is broken down into like these three guiding themes. And within those, in the science side, are guiding questions, and in the space weather side is some focus areas. I'm just going to hit some highlights in just a couple of minutes here. So within the science, right, the first of these themes is this interconnected home. Within it, you can see the guiding questions, right? One of them is about nested system of systems. One is about boundaries within the whole of the heliosphere, and others about how different parts of the system communicate and interact with each other. And CEDAR science is all over this. I know it's an eye chart, but in the table on the right-hand side, I just went through and highlighted, right, where's the CEDAR relevance, or the other primary CEDAR relevance here. And it's up and down. And if you then go to the documents, you'll see a lot of stuff talking about things that are either just on the horizon or just been selected. There's a great discussion here about the need, the scientific need for multi-plane heterogeneous observations, things you can only do with a satellite constellation. So we're going to hear about Daphne in just a moment. This is a great example of this, and how it would work with GDC, which is kind of the necessary multi-plane observations of the upper thermosphere, the topside ionosphere that's responding to that. On the some of the energy inputs, and you can see in the third one there, it's talking about the Aurora, about current systems, right? So this is the real link to EASY, which we just heard about. There's also Ampere, SuperDawn, SuperMag. Take your pick. It's not all just here's the data we need, right? So along with that is a vision for here's some of the models and theory we need to go along with that. Everything from models at the kinetic scale out to the global scale. How on earth you couple these, and I think there is a role for AI in this. How do we take these very small regional, or microphysics models, couple them to large models, not in a traditional sense? Second one, building blocks. So using laboratory in space, and this talks about a couple of things. Very CEDAR relevant. The first is talking about explosive events. So you might think of this as case studies. A great example of this is the Tonga event, which really helped test our models, test our theory, pushes everything out of what we've seen before. Another of these within this is instabilities and how this drives energy exchange and things. And there's great examples there from gold imaging, plasma bubbles that come up, and we've seen since then also, these super plasma bubbles that can reach out across the continental US, and understanding how these all link together. Then the other theme within this, or the other question within this, is on cross-scale coupling. It really talks to the Dashi stuff that we just heard about, and it also talks to Carruthers, which we heard about yesterday. Yeah. 2 more minutes, and I have 2 more slides. It's perfect timing, right? Switching gears, the space weather theme, right? So seeing the relevance of our science to practical and technological applications, and again, CEDAR science and CEDAR-related things are just all the way through this. So this gets broken down into the drivers of the system, within which there's atmospheric forcing, and again, you can think about Daphne, a GDC, everything measuring atmospheric waves as just one example from what we're doing. And then some of the response, so LEO density, Richard talked about this in his talk, and the way we can use our data, but also data assimilation techniques, reanalysis techniques, how you can use models of reanalysis to come back and learn and see what needs improving in our initial physics-based models, and how these two can work together. And then the importance of measuring the state of the system. So think ISRs and all the rest. Couple of other quick things before I finish on this. There's obviously, right, we've seen several slides of this, the importance of low Earth orbit and the impacts of our natural system on it. In the document, there's a great example talking about planning of the TRACERS mission and how some of this had to be redone in response to what we were learning and what was changing. Talks about the role of SWIPSI and how we deal with that. And then finally, yeah, also on the modeling side, and I think within that, something that's important that's in this document is what's coming from AI and ML is not just new tools and techniques, it's also hardware advances, right? And leveraging some of those adapting the codes we have to use the GPUs, which is needed if we want to go to multi-scale models, right? You can't model the entire system at tiny scale with what we've had before. So that is it for my quick summary.
All right, so a quick question for Scott while we're switching over, and Amy, if you could come up here. Nobody has any questions for Scott? We'll have a discussion about the decadal in the workshop led by Phil Erickson, who is here. Yeah, she's just switching over to your slides. Yeah. So the last presentation in this session is about Daphne. So,
all right. All right, I want to first thank Christina and Scott for allowing me to jump in on this session. I am Amy Merkel, and I'm the principal investigator of the Daphne mission that was just selected. So I also want to thank all of you. This is a community win. This is huge. As Larry brought up yesterday, we all need to get behind this. This is our mission, and I want to work with all of you. Our entire science team wants to work with all of you to plan, to make sure that we optimize every single bit out of this mission. So, as I just said, Dynamic is a community resource. I also want to thank the other teams. This has been a long road for all of us, a lot of uncertainty, a lot of perseverance, and a lot of time and effort to represent our community, the ITM community, to NASA. I want to say thank you to Scott and Tomoko and all their teams for all their hard work. Scott and I have been friends and colleagues for over 30 years. Tomoko and I are newer friends, but still we're friends. And we made a pact a long time ago, several years ago, that we were going to work together, and no matter who won, we were going to be completely behind that team, because this is a community, and this is our community win, and this is our community mission. I also want to thank NASA. When I say NASA, I mean the people at headquarters behind the scenes that are pushing to make sure that Dynamic was funded. Asias, John, to name a few, to convince Joe, right, that this was a mission that needed to be funded and needed to be funded now so that we could get vital measurements now. I also want to say that I've been doing a lot of advocating and going up to Capitol Hill and talking to our representatives and really targeting, both sides, Democrats and Republicans, and that science is supported, strongly supported across politics. Everybody is in favor of science, and so I encourage you all to continue advocating for our science, right? They're listening. They passed the 2026 appropriations bill. They're gonna do it again in 2027. They're the people that we need to convince and advocate for our science that it's important. And as I said before, Daphne is a community asset. This is your mission. Join us in planning for the future. And in the workshop coming up in a couple hours, we want to start those discussions. This is our Daphne team and partnerships. The mission management is led by LASP. Spacecraft is BAE Systems. Mighty instrument provided by NRL. There's 2 instruments provided by LASP. And then this wonderful CEDAR community science team. Our project scientist is Brian Harding, and with him pictured here with our newest addition to the team that was born on April 6th. Brian's super sorry that he couldn't be here. I think this breaks his 13-year run of CEDAR, not being able to be here. But we have an incredible team, and I'm charging the team with going out and talking to you all, talking to the community. How can we make the best out of this mission? I also want to say thank you to the team. They nailed it on the science section of our proposal and concept study review. They spent so much time and effort of their free time, because we know scientists don't get paid, doing for proposals, right? And so doing that work to get Aussies and all that for proof of concept. So just briefly, because I only have 1 more minute, but this is just icing of the cake of what Daphne mission is. So Daphne really focuses on dynamics. What are the dynamics sourced from Earth weather and how they propagate up and influence space weather, right? So dynamics are predominant. We know that. We know that we have to get more data, more information about gravity waves, tides and planetary waves on multi-point, multi-scale observations. You need to do that with a constellation. So we have 3 remote sensing instruments on twin satellites. They're identical, right? The thought here is to get up instruments that we know are going to work, to set a baseline so that the newer technologies that we need these newer technologies to get up there and fill the gaps. No single mission was going to solve all the problems. All 3 mission concepts had holes, right? But in this way, by using MIGHTY, build-to-print icon MIGHTY, using a gold instrument, a simplified gold instrument called Plato that Richard Easties actually named, and FUVI, which is a nadir imager. Okay, so this is just an idea, or not the idea, this is the concept, right? And so we have constellation solution. We have 2 satellites going through 3 different mission phases. It's a 3-year mission, all right? So we have Plato observing in the limb. We've got FUVI observing straight down in a nadir point of view, and then we've got MIGHTY picking up the winds. First phase, a string of pearls. So we can do cross calibrations. We can do science with gravity waves. Phase 2 is transitioning, and then phase 3 is locking into that 6-hour local time separation, where we can really define planetary waves and tides. Gravity waves is so exciting. All 3 instruments measure gravity waves. We're going to be able to cover the scale from medium all the way up to large. And we're doing this in a way that we get the horizontal and vertical component of gravity waves all at the same time by overlapping Plato and FUVI observations, as you can see here in this plot. And then we know MIGHTY captures large-scale gravity waves, so we'll be able to get the entire spectrum. Tides and planetary waves, just real quick. These are Aussies done by our amazing science team. On the left is diurnal tides. This is a 5-day window. Truth is on the left, Daphne's on the right. All the way through the diurnal tides. Semi-diurnal is the same way. Planetary waves, the ultrafast Kelvin wave on a 7-day time scale. This is unprecedented, never before done. Really, really excited to bring this to the community. I think my time's up. One more plug. So the Dynago CubeSat is going to be launching in January 29, 2027, so just a few months away. This is a constellation, and it has the FUVI instruments on them. So we're going to get gravity wave, horizontal gravity wave information in just a few months. This is really, really exciting. I wanted to plug this and advertise it, and that is all the time I have left. We have a lot of discussing to do. I really encourage the community to engage, and so that we can make this the best mission possible.
All right, we're going to close this discussion, and I do hope that you're able to join us again in the workshop from 10 to 12. In particular, from 11 to 12, we'll have a discussion with these plenary speakers. So I'm going to hand it over to Lynn.
Thank you very much. The next thing on the agenda is the CSSC announcement and closing remarks. Lynn will be talking about this.
All right, everybody, we are coming to the end of this session and to the end of the workshop. You've got some breakouts, but wow, what a meeting, and what a great way to end this meeting, looking forward. I just love this session that we're looking at, where we're going. We don't even take a breath. We've already done some great science, and we're looking at what's next. So these are my closing remarks. This is the second year we've been in Des Moines. The city is really kind of starting to grow on me, but we're probably going to go someplace else next year. Just a summary of our numbers. We had 240 in-person attendees, 22 remote, 141 posters, with over half of those in our competition. We supported 50 graduate students to attend the meeting, 5 undergraduates, and we piloted a new mentor-mentee program called CEDAR. We had good attendance, good experience, and some lessons learned there. And we all had a great time at the excursion. So the CSSC is the committee that is largely responsible for pulling off the workshop. All of the scientific content is organized by this committee, and here are the members that are rotating off. We are going to miss them immensely, and the members that are going to fill their shoes rotating on. We kicked off the meeting on Monday with a prize lecture given by Shenrong Zhang, who spoke on GNS-enabled discoveries of traveling ionospheric disturbances. That was a wonderful way to start the meeting. And our pilot program was lively. We had all of these different tables of mentors and mentees meeting and speaking together. We learned some things, and we hope that this is a program that will continue on in the years to come and get better and better as we move along. We heard from our agencies. We had NASA and NSF here a lot of the week in person, and we had great poster competitions with really great catered food and wonderful discussions. Our excursion was fantastic. There wasn't even a hint of rain. We had a lot of people go, have a lot of fun, and instead of losing 12-0, we only lost 11-10 in extra innings. So that was a lot of fun too. Midweek, we moved on to our inaugural Early Career Prize lecture given by Jack Wang, who talked about wave-driven circulations in the lower thermosphere. This is a really great prize that honors early career scientists, so I'm really glad to institute this tradition in the CEDAR community. Throughout the week, we heard from our Grand Challenge, 3 Grand Challenges in both breakout sessions and in plenaries and panel discussions. We've got Sudha Kamali in year 1, leading a Grand Challenge on space weather prediction. We've got Leslie LaMarche in year 2, leading a Grand Challenge on polar cap patches. And we've got Jens Oberheide in year 3, leading a Grand Challenge on lower atmosphere impacts on the IT. If you just saw Romina's talk on how we're doing representing our CEDAR thrusts, I'm really interested to see a new Grand Challenge next year that widens that sliver of data, that data mining category, maybe something AI or something along those lines that's kind of strategic. So I'll be pinging some of you, and we'll have discussions later on. We had 5 science highlights sprinkled throughout the session that were really exciting, where we heard novel research from our community. Our student poster winners were really exciting, and I would show you the group photo, but it turned out kind of weird with a light through all of their foreheads, so that wasn't flattering, but congratulations to all of our students who won prizes in our poster competitions. We had excellent posters this year, as we do every year, and I continue to be impressed with our next generation. Larry Paxton gave perhaps one of the most unique, distinguished lectures that I've ever heard, where we actually got to choose between which talk we could hear. We chose the red pill, and Larry shared unique, valuable scientific survival tips that I'm going to probably go back and study in order to survive the next couple of years. Thank you, Larry. Last night, we had a really fantastic banquet. The food was delicious, and the entertainment was a lot of fun. I'm not sure who this IT member was because they've got a mask, but just the teams were so creative and really got into it. We all had a lot of fun playing Family Feud one more time. So we finally put a little fishbowl out on the registration desk to collect your feedback, and Li Ying sent an email announcement soliciting your feedback. We really need your feedback. It's an important step in this workshop in order to make things better each year and to fix problems, correct wrinkles that happen, and challenges that we are faced with. We heard that we should, maybe have a more flexible deadline with the mentor-mentee program and make sure that instructions are really clear in terms of how students should upload their posters for the competition. Maybe group sessions by topic so that people can better attend the workshop for a few days if that's what fits their schedule. And I agree with this last one, maybe starting the meeting a smidge later. I'm not a morning person, so I'm all for the 9 a.m. start, but please give more feedback. We take it seriously. The CSSE talks about it at length, and we implement fixes. We listen to you, so please let us know what you think. I just want to shout out to our student representatives. They did an absolutely stellar job pulling off Student Day and looking after all student-related aspects of the workshop. These are students who are, doing their PhD work and have a full load, and then also do an immense amount of service, something similar to a mid-career scientist. And we ask a lot of them, and they deliver. And a special thank you to Bryce, who really went above and beyond for Student Day, led our CEDAR mentor-mentee program, led student demos, volunteered for the Family Feud game at the last minute, and more. Your dedication is inspiring to me. There's so many thank yous, too many to call out people individually. It's a team effort. It takes a village. There are probably 50 people who are behind the scenes that do tons of different organizational aspects of this workshop. It's a heavy lift, but we pull it off for you, and we really hope that you had a good time this week. Next year, we will be someplace else. We're already starting to plan, so no rest for the weary. We didn't even exhale 1 second. Yesterday, we started looking at new venues and their attributes, and we hope to take you to a new location somewhere in the U.S. and have a great workshop next year. Thank you.
Ning, are you going to take any questions from the audience?
Well, I'm going to suggest a question, which is, how much can we thank Lynn for 3 years of being CSSC chair?
I've got 1 more year at the helm, and I'm not going to waver. I'm dedicated to this community. I'm not rotating off quite yet.
But you're not chair anymore.
I am chair for 1 more year.
Okay, I take it back.
I will,
I take it back.
I will pass the torch to Scott. I will happily pass the torch to Scott England. This time next year, he'll be giving closing remarks.
Do we have any questions, comments? Anything about the meeting? Sounds like we had a wonderful meeting. Yeah, thank you so much. So.